Imagine you're standing in a massive, brightly lit room, and stacked on every single table, just covering the floor, are thousands and thousands of index cards.
Oh, wow.
Yeah, 5,000 to be exact. And on each card is just a number. Raw data.
That sounds completely overwhelming.
Right. Staring at it, you feel a little dizzy. You can't possibly hold all those individual numbers in your head, let alone, figure out what they actually mean.
No, nobody could.
And that feeling of being completely overwhelmed by data, that is exactly where we are starting today's deep dive.
It really is the perfect place to start.
Because today, we are taking a stack of notes and research on statistical methods and measurement, and we're going to decode it for you.
Yeah, and that feeling of drowning in numbers, that is the baseline reality for almost anyone trying to measure the world. I mean, think about what a researcher actually does on a daily basis.
Like they're collecting data constantly.
Exactly. A psychologist might be in a lab tracking the micro movements of an infant's eyes as they look at a new toy. Or they could be out in the field recording heart rates of people experiencing high stress.
Or counting the exact number of trials it takes to condition a monkey to do a task, right?
Yes. Or even tallying up how many patients show real improvement after a particular type of psychotherapy.
And every single one of those scenarios just ends up generating a mountain of raw numbers.
A literal mountain. Interpreting that mountain is the core challenge. Like, how do you go from a pile of erratic heart rate readings to a definitive conclusion about human stress?
You need a system.
You do. Basic statistics is the only life raft available there. It's the discipline of collecting that numerical data and, crucially, figuring out how to make valid inferences from it without, completely fooling yourself.
Okay, so let's unpack this. Our mission for you today is simple. By the end of this deep dive, we want to take you from someone who might feel intimidated by a wall of raw data to someone who can confidently read between the lines of any scientific claim you see.
Which is a very handy skill to have.
Definitely. We're going to give you the tools to see the hidden shapes inside the numbers. So let's go back to those 5,000 index cards. Say they're university entrance exam scores sitting in a registrar's office.
Okay, yep.
Before we can analyze them, we just need a shorthand.
And that shorthand is what we call descriptive statistics. Because thumbing through 5,000 cards gives you absolutely no real insight. Your brain just can't process it.
No, it's just a blur.
So the very first step is always grouping the data to force it to take a shape. We do this by creating a frequency distribution.
Which is basically just sorting things into buckets, right?
Pretty much, yeah.
Like if the scores go from 0 to 100, you create 10-point buckets, 50 to 59, 60 to 69, and so on.
Exactly.
You count how many cards fall into each bucket, and suddenly that chaotic pile starts to look like a skyline.
And if you draw bars for each bucket, where the height of the bar is the number of students, you get a histogram.
Which is great because you instantly see where the bulk of the people landed.
Right. But visually seeing the shape is only step one. We still need a numerical way to talk about the center of that skyline.
A representative point.
Exactly. A point that summarizes the data, which brings us to measures of central tendency. The big three here are the mean, the median, and the mode.
Now, I feel like anyone who has taken a math class knows the mean. It's just the arithmetic average.
Yep. Add them all up and divide.
And we know the median is the absolute middle score if you lined everyone up from highest to lowest.
Right. And the mode is just the most frequent score.
So in a perfectly symmetrical world, those three numbers are exactly the same, right? They sit perfectly in the center.
They do. But the real world is messy.
Very messy.
What's fascinating here is what happens when the data is unbalanced or skewed. When that happens, those three measures of central tendency suddenly break apart. They separate from each other.
Oh, interesting.
And understanding why they separate is essentially a superpower for seeing through bad data.
Okay, let me throw an analogy at you that I always think about with skewed data.
Go for it.
Think about a morning commuter train scheduled to leave at 8 a.m.
No.
Most days, it leaves exactly at 8:00. Occasionally, it gets delayed by something on the tracks and leaves at 8.07 or maybe even 8.22.
Sure.
But it never, ever leaves early, because they aren't going to leave passengers stranded on the platform before the scheduled time.
Oh, that is a perfect illustration.
Right.
Yeah, you have a hard floor at 8 a.m., but a long, thin tail of occasional late times stretching out to the right.
Exactly.
And because of those few really bad delays, the mean, the arithmetic average of all the departure times is pulled upwards. So the mean might be 8.04 or 8.05.
But the median doesn't move much.
Barely at all. The
Yeah.
literal middle value of all those departures is hardly affected. It might still be 8.02,
Hmm.
and the mode is still exactly 8.00.
So those extreme outliers drag the average up, but the median just barely blinks.
Yep.
This is where you start to see how math can be, like, weaponized.
Oh, absolutely.
Let's say you have a company where the top executives are making astronomically high salaries, way off at the top of the scale.
Millions of dollars, sure.
And the company decides to slash those executive salaries significantly. But at the same time, they give a very small, like 2% wage increase to the thousands of regular floor employees.
Okay, think about what happens to the math there. Most people in the building got a raise.
Right.
So the absolute middle person in the company, the median worker, their pay went up. The median income rises.
But because those few executive salaries were so incredibly massive to begin with, chopping them in half pulls the overall arithmetic average of the entire company down.
Exactly. The mean drops, even though the median rises.
Okay, so if the workers' union wants to go to the press and argue they're being mistreated, they quote the mean and say average incomes at this company are dropping.
And if the executives want to defend themselves, they quote the median and say, "What are you talking about? Average incomes are rising."
So I have to push back here. Are either of them technically lying to the public? Or are they just weaponizing the math?
Well, neither of them is technically lying. They are both using a mathematically valid measure of central tendency.
But it's super misleading.
Completely. Because they're relying on the fact that the public assumes the word average always means the same thing. They just pick the statistic that tells their preferred story.
Wow.
Which is exactly why knowing the middle of a data set is never enough. It leaves you completely blind to how spread out the rest of the group is.
So the median protects us from being tricked by extreme outliers, but it still doesn't tell us what the extremes actually look like.
Right. And to find that out, we need measures of variation.
Okay.
Imagine you're a clothing designer, tasked with creating outfits for a huge group of people, but you aren't allowed to take their precise measurements.
That sounds like a nightmare.
It is. You just get a summary on a piece of paper. If that paper only gives you the average size of the group, you're in serious trouble.
Because the average could mean anything.
Exactly. You might design everything for an average height of 5'9", only to show up and realize half the group is 5 feet tall and the other half is 6'6".
So literally no one is actually average.
Right. To design the clothes, you need to know the spread.
Let's apply that to a classroom. Imagine two different university classes, Class 1 and Class 2. They both take the same exam, and they both have the exact same mean score of 75.
Okay.
But in Class 1, every single student scored between a 73 and a 77. They're clustered incredibly tightly.
Very consistent.
But in Class 2, the scores are totally chaotic. Some students got a 60, others got an 85 or 90.
So the average is 75 in both rooms, but the reality of teaching those two classes is entirely different.
Exactly. So we need a mathematical yardstick to measure that scatter.
We do.
And, you know, if you're listening to this while driving or cooking, you might be thinking, well, why not just use the range? Highest score minus lowest score.
It seems intuitive.
Right. For Class 1, the range is 4 points. For Class 2, the range is 30 points. Simple, right? But researchers rarely just use the range.
No, they don't.
They use variance and standard deviation. And honestly, the math behind variance can feel unnecessarily complicated.
It can be a lot.
Like, you find out how far every single score deviates from the mean, and then you square all those numbers. Wait, why are we overcomplicating this by squaring all the numbers just to take a square root a minute later? Why doesn't the simple range work?
I know it feels convoluted, but there is a profound logic to it. The simple range only looks at two numbers, the absolute highest and the absolute lowest.
Okay.
It completely ignores what the other 98% of the group is doing.
Oh, true.
Like, you could have a class of 50 students where 48 people score exactly 75, one scores 0, and one scores 100.
So the range is a massive 100 points.
Exactly, making it look like a chaotic class.
Yeah.
But almost everyone is actually identical.
Yeah.
Variance is powerful because it accounts for every single score in the data set. It measures how far every individual departed from the mean.
But why square the deviations? Like, if I scored 5 points above the mean, why turn that into 25?
To get rid of negative numbers.
Oh, I see.
Yeah, if you score 5 points above the mean, that's a +5. If someone else scores 5 points below, that's a -5.
Right.
If you just added those up to find an average deviation, the positives and negatives would just cancel each other out to 0.
Yeah.
It would look like there was 0 variation.
That makes total sense. So by squaring them, a -5 times a -5 becomes a +25.
Exactly. Everything becomes positive. You average all those squared deviations together, and you get the variance.
Okay, that makes sense for keeping the numbers positive. But because you squared them, the variance is now in this weird, inflated, alternate reality. Like it's measured in squared test points.
Which is completely unhelpful for a real-world researcher.
Yeah.
So to bring that inflated number back down to the original units of measurement, you just take the square root of the variance.
And that's standard deviation.
Yes, represented by the Greek letter sigma. It tells us, on average, how much the scores in our dataset tend to vary from the center. So Class I has a tiny standard deviation. Class II has a large one.
So what does this all mean? We can now perfectly describe the specific data we have sitting in front of us on those 5,000 cards. We know the center and we know the spread.
We do.
But here is the massive leap every researcher has to make. How do we know if our specific stack of cards actually represents the real world?
This is the border crossing from descriptive statistics into statistical inference.
Okay.
And to understand it, we have to distinguish between a population and a sample. A population is the total supply of whatever data you're studying.
Like the census.
Exactly. When the UK Office of National Statistics does a census, they are trying to measure the entire population of the country. But a population could also be every temperature registered on a thermometer over a decade, or, every word spoken in a city today.
But most of the time, getting the entire population is completely impossible. It's too expensive or too time-consuming. So we take a random fraction, we take a sample.
Yeah, because a sample is just a fraction, it will never perfectly mirror the whole population. It will always contain what we call errors of sampling.
That sounds bad.
Well, it isn't a mistake the researcher made. It's just the built-in, unavoidable uncertainty of not looking at the whole picture.
Right, because you didn't ask everybody.
Exactly.
Yeah.
If you take 10 different random samples, you'll get 10 slightly different averages. So the fundamental question of science is, how do we make reliable inferences about the whole population when our sample is inherently flawed?
And this is where we bring in the heavy hitter, the normal distribution. The bell curve.
Yes, the bell curve is the mathematical representation of how things naturally distribute when they're the result of many independent chance events.
So for you listening, picture a giant game of arcade pinball.
I love this analogy.
You have a massive board held vertically, and you drop hundreds of little steel balls from the top center. As they fall, they hit a series of pegs. At every single peg, it's pure 50-50 chance whether the ball bounces left or right.
Just total unpredictable chaos for every individual ball.
Right. But by the time all the balls hit the collection compartments at the bottom, they pile up in this perfectly predictable symmetrical shape. The highest pile is right in the middle, and it tapers off smoothly to the sides.
It's beautiful, really.
It completely blows my mind that individual chaotic chance events inevitably create a perfectly ordered mathematical shape.
It is one of the most profound realities of nature. Most things fall near the mean, and very few hit the extremes.
Right.
And because the bell curve is mathematically perfect, we know exactly how the area underneath it is divided up, measured in our new friend, the standard deviation.
And the magical percentages.
Exactly. In a normal distribution, roughly 68% of all cases will fall within plus or minus 1 standard deviation from the mean.
Okay.
95% of cases will fall within 2 standard deviations. And virtually everything, 99.7% of cases, falls within 3 standard deviations.
So going back to our university entrance exams, let's say we know the whole population's mean is a score of 75, and the standard deviation is 10 points.
Yep.
If you score a 90, we don't just say you got a 90, we can convert that into a standard score. You are 15 points above the mean. Since the standard deviation is 10, you are exactly 1.5 standard deviations above the mean, plus 1.5 sigma.
And if you score a 53, you are 22 points below the mean, making your standard score minus 2.2 sigma.
Makes sense.
Standard scores are brilliant because they create a universal currency. They let us instantly know exactly where you rank compared to the rest of the world, regardless of what the original test was out of.
Okay, we've got our bell curve, we've got our samples, but because every sample has that built-in error we talked about, if we run a psychological experiment and see a difference between two groups, how do we know if we've actually discovered a real psychological truth or if we just got a weird bounce of the pinball?
That is the core problem of experimental research.
Right.
To solve it, we calculate the standard error of the mean. Basically, we estimate how many our sample mean is likely fluctuating from the true invisible population mean.
Okay.
Crucially, the standard error shrinks as your sample size grows. Asking 1,000 people will always be more trustworthy than asking 10.
Let's apply this to a real scenario. Say you run an experiment comparing the grip strength of left-handed men versus right-handed men.
Right.
You take a tiny sample of 5 right-handed men and 5 left-handed men. The right-handed group averages 58 kilograms of strength, and the left-handed group averages 50.
Okay, that's an 8-kilogram difference.
Right. Can we immediately conclude right-handed men are fundamentally stronger?
We absolutely can't,
Right.
because we don't know the variation.
Right.
Consider 2 different ways that average could happen. In the first scenario, 4 of the right-handed men are completely average, scoring around 47 kilograms. But the 5th guy happens to be a competitive powerlifter who grips 100 kilograms.
Oh, wow.
Yeah. He single-handedly drags the entire right-handed average up to 58.
That 100-kilogram outlier is a massive red flag.
Huge.
The difference between the averages is 8 kilograms, but it's wildly unreliable because the data is incredibly scattered. The signal is just being completely drowned out by the noise.
Exactly. But imagine a second scenario. The 5 right-handed men score 56, 57, 58, 59, and 60.
Okay.
The lefties score 48, 49, 50, 51, and 52.
So the average difference is still exactly 8 kilograms, but this time the variation is tiny.
Every single right-handed guy beat every single left-handed guy. It's incredibly consistent.
So the consistency is the key.
Yes, it tells us we can't just look at the raw difference between 2 means. We have to compare that difference to the variability of the data.
How do we do that?
We do this by calculating a critical ratio. You take the difference between the 2 means and you divide it by the standard error.
Oh, so it's essentially a signal-to-noise ratio. The difference is the signal. The standard error is the noise.
Perfectly said. If the signal's way bigger than the noise, you found something real. And here is where we hit the golden rule of modern research.
Okay, lay it on us.
For a difference to be considered statistically significant, that critical ratio needs to be 2.0 or larger.
And the reason it's 2.0 comes straight back to our bell curve, doesn't it?
It does. A standard score of 2.0 or higher only happens about 5% of the time by pure chance.
Oh, wow.
So if we calculate a critical ratio of 2.0, we know there is only a 5 in 100 probability that this difference was just a fluke of sampling error.
Okay, for instance, if you test reading levels in 6-year-olds and the boys' average is 70, while the girls' average is 72, it's just a 2-point difference.
Right, very small.
But if the sample sizes are huge and the variance is tiny, yielding a critical ratio of 4.0, you can definitively say girls scored better.
Yes, you can.
But hold on, I'm stuck on this 5% rule. I have to push back here.
Okay, what's on your mind?
We just accept that it's a 5% chance of being wrong. Isn't an arbitrary rule that allows us to publish a completely false scientific claim 5 times out of 100 a little, I don't know, dangerous?
Well, this raises an important question, and it's one the scientific community argues about constantly.
I would hope so.
Yeah. Yes, at a 5% significance level, 1 in 20 published experiments will show a significant result that is entirely a fluke.
That's a lot.
It is, but that is the fundamental cost of doing business with samples instead of whole populations.
Yeah.
The 5% level is just a historical convention.
Oh, so it's just arbitrary but
Yeah.
convenient.
Basically. Now, in high-stakes fields like testing a new pacemaker or a life-saving drug, researchers don't accept 5%.
Good.
They might demand a 1% or even a 0.1% level of significance. You just have to decide how willing you are to make a catastrophic error.
Okay, so we've established how to prove 2 groups are genuinely different and how confident we can be in that difference. The final piece of the puzzle is measuring if 2 traits actually move together.
Right. We want to know if there is a parallel variation between 2 measures. Like, if I score high on my university entrance exam today, will I score high on my final grades 4 years from now?
And to measure this, we use the coefficient of correlation.
Yes, represented by the lowercase letter r.
And R operates on a sliding scale from positive 1.00 down to negative 1.0.
Correct. A positive 1.00 is a perfect positive correlation. They move in lockstep.
So if you go up 1 point on the entrance exam, your grades go up by exactly a mathematically predictable amount.
Exactly. And a negative 1.00 is a perfect negative correlation. As 1 goes up, the exact same predictable amount goes down on the other side.
What about 0?
A 0.00 means absolute random chaos. Knowing one trait tells you absolutely nothing about the other. It would be like trying to predict someone's intelligence based solely on their shoe size.
So if you look at a scatter diagram predicting freshman grades from entrance exams, you plot the exam score on the bottom x-axis and the grades on the side y-axis.
And usually you see a clear diagonal trend.
Right. You'll see a dot for a student named Adam who got the highest test score and also the highest grades. Way down in the other corner, there's Edward, who got the lowest test score and the lowest grades.
And when you run the math on how all those dots deviate from the center, you might get an R of positive 0.85.
That's high.
It's not a perfect 1.00. There's always some scatter, a few students who buck the trend. But plus 0.85 is a very strong positive correlation. It proves the entrance exam is actually doing its job as a predictor of success.
Here's where it gets really interesting, though,
Okay.
because this brings us to what is probably the most frequently violated rule in all of science journalism.
Oh, I know where you're going with this.
Correlation does not imply a cause and effect relationship.
It is the ultimate trap.
Where?
Just because two variables move together beautifully on a graph, we absolutely cannot conclude that one causes the other.
Right.
They might both be caused by a third hidden factor that we aren't even measuring.
Think about this paradox from the data. The correlation between the amount of time a university student spends studying and their actual final grades is often slightly negative, around negative 0.10.
Yep.
So by the logic of causal correlation, if you want straight A's, you should immediately drop your books, walk out of the library, and never study again.
Which is obviously an absurd conclusion.
Obviously. But why?
The negative correlation is mathematically real, but the assumption of causation is entirely backwards. The hidden variable here is the student's baseline level of preparation or natural aptitude for the subject.
Of course.
Better prepared students simply don't need to study as many hours to master the material and get good grades. On the flip side, students who are really struggling with the material might spend hours and hours agonizing in the library, but they still end up with lower grades on the exam.
So the act of studying isn't causing the bad grades.
No. The underlying difficulty with the material is causing both the low grades and the high study time.
That perfectly illustrates why we have to be so careful with data.
Absolutely.
Well, we have covered an immense amount of ground today. We started by taking a chaotic mountain of 5,000 raw index cards and learned how to tame them, grouping them into histograms and finding the center.
We learned why averages can be dangerously misleading if you don't know the spread of the data.
Which led us into the math of variance and standard deviation. And we realized that our samples are never perfect. But by relying on the mathematical magic of the bell curve, our pinball machine of chance, we can calculate standard errors and signal-to-noise critical ratios.
We also learned the 5% rule to prove our findings aren't just random flukes.
Right. And finally, we explored how correlation measures the relationship between two traits, while serving as a stark warning that parallel movement does not mean one thing causes another.
It really is a lot to take in, but it does change the way you look at numbers forever.
It totally does.
And if we connect this to the bigger picture, it's about being an active, defensive consumer of information.
Oh, I like that.
So I'll leave you with this to think about. If an arbitrary 5% chance of being completely wrong is the accepted gold standard for statistical significance, and if correlated data can easily trick us into thinking that studying makes you fail. Think about the last time you scrolled past a sensational news headline claiming that a certain common food causes a deadly disease. What hidden variables were those researchers missing while they desperately scoured their data just to find that 5% critical ratio?